Thank you, and good afternoon to everybody. The topic I will talk about today is relating to a technology which, by the way, is a very old technology, but it has been discovered very recently due to energy efficiency necessities. In fact, based on empirical observation, even without knowing the basic physical principle, humankind has used since from the third millennium before Christ the evaporative cooling to mitigate the temperature of spaces, particularly in areas with a hot and dry climate. It was invented in ancient Egypt, for example. Only over the last 2 centuries, scientists have studied the basics of thermodynamics and processes related to the exchange of sensible and latent heat, and found the theoretical principle of cooling by evaporation, which, however, has played a marginal role in the recent past due to the extensive use of mechanical refrigeration systems. The water evaporation process, as any element, water assumes the solid liquid gaseous state in function of the internal energy of the molecules. That occurs as vibrational, rotational, translational motion and reciprocal collisions. The temperature is a measure of the average internal energy, and therefore, the higher the temperature, the greater the internal energy of the molecules. Upon an energy input, liquid water molecules increase their internal energy, and part of them reaches an energy level sufficient to enter into the evaporation process, overcoming the attractive forces of the bulk of the liquid, passing to the gaseous state, becoming vapor, and spreading in available space around. The vapor molecules, due to their kinetic energy, exert over the contiguous bodies a macroscopic pressure proportional to the number and to the force of the collisions, as well as the internal energy. Also, vapor pressure depends on temperature. In this diagram, we show the pressure exerted by the water vapor molecules versus temperature just above the surface of liquid water. In this condition, water vapor is in equilibrium with its condensate state, and therefore that pressure is said saturation pressure. Leaving the liquid water and entering into the atmosphere, the vapor molecules must compete with the pressure exerted by the other gases. In fact, the atmosphere contains is a mixture of dry air made by oxygen, nitrogen, argon, and other gases, and vapor, and there's more or less all over the world an atmospheric pressure at sea level, which is equal to the sum of the individual pressure of the several gaseous components. Any gas has a pressure, which is called partial pressure, and the number of molecules of water contained into the air is proportional to the vapor partial pressure. Of course, the maximum quantity of water into the air is got when the vapor partial pressure equals the saturation pressure. In this condition, the air is said saturated. However, differently from permanent gases, whose relative percentage is stable, water vapor concentration varies with time, location, and weather. In this diagram, for example, we can see that at the same temperature, in the diagram it is 25 degrees centigrade, we may have saturation, the upper point, but as well we may have a lower content of vapor, so that the quantity of vapor really contained in the air is lower than the saturation one. Well, the relative humidity is just the quantity of real vapor, or the pressure, the vapor pressure, versus the maximum pressure, the pressure we have in saturation. The vapor pressure deficit is the difference between the actual vapor pressure and the saturation one, and indicates the maximum capability by the air to absorb additional vapor at the temperature. So if the relative humidity is not 100%, the air has the capability to absorb some water molecules. The vapor content in the atmosphere is called absolute humidity and is expressed as mass of water per unit mass of dry air. And the absolute humidity is function exclusively of the vapor pressure. Another important parameter of humid air is the enthalpy, which is the content of heat, of energy under the shape of heat, which the air contains. And also this depends on temperature and on absolute humidity. So water liquid molecules require an heat input, as we have seen, to increase their internal energy in order to pass to vapor. And this heat can be given by an external source, for example, the sun, electricity, or burning a fuel, as it happens normally during humidification. Alternatively, the evaporation heat can be supplied by the air itself, without any external energy input. The molecules evaporating absorb heat from the entire air liquid vapor system, which then, to supply this energy to the vapor, will decrease the temperature. The process is therefore defined adiabatic, which means without transfer of heat, and is enthalpic because the heat content of air being humidified does not change. Just for the same reason, this process is defined adiabatic cooling. In this basic diagram, it is shown how an adiabatic cooler works. In it, an airstream is circulated over an extended water surface with which the air comes into close contact. And within the cooler, the airflow causes the evaporation of water, which is contained into the pad, into the cooler. The psychrometric chart we see here is as we know, the diagram of the state of humid air, shows that it is possible to make many processes, heating, cooling, humidification, but the most important for us is the green one, the green arrow, in which we see the adiabatic cooling following an isenthalpic line, in which we have the increase of humidity, which is shown on the vertical axis, but in the same time also a decrease in temperature. So by evaporating water, in fact, we decrease the temperature of the air. And just to give you an idea, per each 10 kilograms of water per hour we evaporate, we get a approximately 7 kilowatt cooling effect without employing any energy, as it happens with a normal refrigeration system, which in this case would require 2 kilowatts, for example. So it is very important for energy conservation. This is adiabatic cooling. We can see here that due to the difference between the vapor pressure over the water surface, which is evaporating, and the partial vapor pressure of unsaturated air being humidified, the evaporation of water will take place. The lowest temperature theoretically attainable corresponds to the intersection between the isenthalpic line followed along the process and the saturation curve. And this is represented by the black arrow in the graphic. So here we have, for example, air starting from 38 degrees centigrade and 20% relative humidity, and following the isenthalpic line, it will arrive up to 100% relative humidity, with a much lower temperature. This is the vapor pressure deficit, starting from the highest point and arriving to zero when the air is saturated. This is relative humidity starting from 20 to 100%, and this is the cooling effect I get along the humidification. In fact, there is the saturation effectiveness. In the evaporation of water involves, this is very important, involves a simultaneous transfer of heat and mass, the evaporating molecules, between the airstream and the liquid surface. The heat exchange is proportional to the temperature difference, when the mass exchange is proportional to the vapor pressure difference, and the rate of both depend linearly on the interface area between water and air. However, along the process, this temperature and vapor pressure which cause these transfers the differentials between humid air and water sharply decrease, making the saturation of living air hardly achievable in practice, so that any adiabatic cooler will have a saturation efficiency which is the ratio between the real temperature difference we reach versus the theoretical temperature difference got with the complete saturation. The adiabatic cooling requires air changes. It is very efficient because, when practicable, produces a cooling effect with no energy consumption. An evaporative cooler designed for air conditioning purposes reduces the processed air temperature but increases the humidity of the air. Therefore, room air conditioning by means of an evaporative cooler is not viable, just recirculating the air in the same ambient. In this case, because very soon the air would become saturated and therefore the process would stop. On the contrary, it requires the introduction of outside air to which obviously must correspond an equal rate of exhaust air. So the air enters from here and goes out from there. And of course it passes through the evaporative cooler. Evaporating cooling equipment can be direct or indirect. The direct evaporative cooling causes the cooling of the air which is taken from outdoor and introduced straight into the space. Basically, the outdoor air enters from here, is humidified and adiabatically cooled here and sent directly into the ambient. Some of the air is recirculated, and normally a conjugated damper system will proportion the quantity of recirculated air and cooling air, outdoor air, according to the capability of the environment to supply a cooling effect. Of course, this is possible whenever the temperature of the outdoor air downstream the adiabatic cooler, so in this position, is lower than the indoor temperature. And in fact, for the same airflow, the cooling capacity is proportional to the airflow rate and to the difference between the two temperatures. Indirect evaporative cooling is less efficient, but it is required whenever, for pollution reasons, we do not want to introduce the outdoor air directly into the environment. So in this case, the exhaust air is passed through an evaporative cooler and then through a heat exchanger, when the outdoor air crossing the same heat exchanger is cooled down by the exhaust and cooled air. In both cases, direct and indirect, there is the possibility also to control the humidity, in which case the adiabatic cooler is working as a humidifier in wintertime, when there is no necessity or possibility of having a cooling effect. Which are the most used adiabatic coolers? Well, first of all, they must have enough air velocity to create a sufficient turbulence and the removal of water molecules from the water surface. So they must create a certain turbulence. And they must have enough interface surface between the air and the evaporating water in order to allow the mass and the heat transfer. The most used systems are the wet media humidifiers. In these adiabatic humidifiers, the air is passed through wetted pads, which are made by honeycomb structures of resin-impregnated cellulose or glass fiber, offering a very wide interface area. The pads placed vertically, like this one, are kept wet by a water flow distributed over the upper edge. In ducted air conditioning system, ventilation system, wet media humidifiers are generally placed inside of air handling units, and the wet pad is made normally using modules like the one we see on the back on the right. But in these systems, Only part of the water drawn from a bottom tank by a recirculating pump and distributed onto the pads evaporates when the rest is recirculated. So in this system, we have here a water reservoir, and with a pump, the water is circulated over the pad. Approximately 10% of it is evaporating, but 90% returns back to the reservoir and recirculated again. The evaporation process, however, increases the concentration of salts which may build up on the surface, forcing to clean and replace the pads when clogged. Furthermore, they should be particularly controlled because the presence of a warm water recirculation potentially promotes a risky bacterial growth, because warm water with high salt content are particularly favorable to the growth of bacteria like, for example, Legionella. Last but not least, the airside pressure drop of the pads requires an additional energy consumption even when no humidification is needed. We have seen just we learned from the previous speaker that additional pressure drops into the system is an energy consumption because it has an additional pressure drop which is to be also when the humidification or the adiabatic cooling is not required. So you keep recirculating the air through a parasitic pressure drop also when it is not needed. The use of wet media humidifiers, widespread for the limited price, should be carefully evaluated, looking also at the operating costs, which sometimes are not so low. High-pressure atomizing systems are equipped with a volumetric pump which pressurizes the water to values between 70 and 100 bars and delivers it to small nozzles that produce a fine mist, easily absorbed by airstream because the surface offered by 1 liter of water atomized at 15 microns is as high as 400 square meters. The distribution piping network that supports and supplies the nozzle is positioned in an air duct, like in this case, or placed directly into the environment to humidify, like that, on the ceiling. High-pressure atomizing systems may reach an excellent level of accuracy of the humidity in the controlled space and very high capacities with a negligible electric consumption absorbed by the pump. And under the hygienic aspect, they are not critical because do not promote bacterial growth. In fact, in the case of direct humidification into the environment, the sprayed water is fully absorbed by the air. And in ducted systems, the fraction not evaporated, which is usually very small, is drained without any recirculation. The last type of humidifier I will mention is the family of ultrasonic humidifiers, which provide an extra fine atomization of water by means of the high frequency vibration of piezoelectric elements, and the absorption of water is immediate due to the wide interface surface because 1 liter of water atomized at 3 microns diameter offers 2,000 square meters of surface through which the water is vaporized. The best ultrasonic humidifiers reach exceptional levels of precision, plus or minus 1%, in the entire range of their rated capacity. And thanks to the high efficiency of the absorption, they are suitable for the distribution of the produced mist directly into the room as well as in ducted system. So these are units for ducted system, these are directly for the ambient, and these are very small units for fan coils. Due to the size and cost, they are convenient, particularly for small and medium installation, up to 15 kilograms per hour. Now, to finish, I will mention some few case studies which may be of interest. This is the diagram of a data center in UK belonging to a very big worldwide corporation in which has 180 global data centers with enormous production of heat. In this case, the air coming from the data center, hot air, is passing through a corridor, and with the spray humidifiers, it is cooled down and returned back, whenever cooled, to the data center itself. Also in this case, of course, due to or according to the environmental conditions, outdoor conditions or indoor conditions, there is the possibility with conjugated dampers to regulate the percentage of recirculated air and fresh air. Because in wintertime, for example, it is not necessary to cool down the air adiabatically. It is enough to take air from outdoor. Of course, some humidification is required to keep the humidity level at the minimum required level. This is the view. This is the corridor we have seen in the diagram. These are the pumping stations, and this is the conjugated damper wall. A second important, interesting application of evaporative cooling is in air-cooled heat exchangers. Here we see, for example, that in heat exchanger like condensers or water coolers, air-cooled water coolers, we have the possibility to humidify, to cool down the air adiabatically before the air enters into the finned coils. In this case, the enter will be lower. The temperature of the entering air is lower than the ambient air because it is cooled adiabatically. But in addition to that, the water may be sprayed in excess in order to wet the finned coil, so promoting a further evaporation during the heating along the heat exchangers. So by getting up to 10 degrees centigrade lower condensing temperature in dry climates and hot climates. This is another case in Madrid, in the subway station. In crowded periods, in hot days of the year, the temperature into the subway is extremely high. So they decided to test the possibility to cool down the temperature inside the station simply by humidifying the air, so cooling it adiabatically. Well, the result was very good because during the 3 hottest months of the year, they got a decrease of 3.5 degrees centigrade versus other comparable stations in Madrid, with a very, very low energy consumption. And due to the dry climate, the inside relative humidity never exceeded 70%, so with an extremely good and satisfactory result. Industrial application, in this case, we are in a very big petrochemical station where they produce energy with a turbine, electrical energy with a turbine. The energy in a turbine is proportional to the mass of air which is introduced into the turbine. And the mass of air is, of course, decreasing with the increase of temperature. So in order to keep high enough the efficiency of the turbine, with the adiabatic cooling, it is possible to pre-cool the air before entering into the compressor of the turbine. And in this case, it is possible to save 1% of energy per each degree centigrade of temperature. So, being this in Middle East, it is possible in summertime to increase the capacity of the turbine up to 15%, which is a lot. And this is the basic diagram. This is the pumping station. This is the inlet of the air, and this is the turbine. The last 2 examples, one which is very close to you, this is the Greek opera, in which it has been installed some pumping stations with high-pressure atomizing systems to control the humidity and to keep it high enough in order to prevent the health of the singers and of the audience, and also to prevent the damage to the wooden instruments. The last one is, well, not the last, almost the last one, is a very nice application with painting booths. Now, the solvent, the synthetic solvent in painting techniques in automotive and also in the airplane industry is being substituted by by water. So it is a water-based paint, which is extremely sensible to the relative humidity of the air which is injected into the booth. So it is absolutely necessary to keep the tolerance of the humidity plus or minus 2%. And this is got, as you can see, the system was started at this point, and from there the humidity and the temperature was kept absolutely flat. Last case, I promise, is a humidification in a museum in Venice. In this case, the humidification made with ultrasonic humidifiers placed inside the fan coils are keeping the level of humidity within tolerances to protect the artworks there inside. But in the same time, it also gives a cooling effect during the summer, which in Venice is maybe sometimes very high. That's all. Thank you very much.
Thank you very much. It's amazing how natural processes and physical processes and know-how that date centuries back and with new technology millenniums back can be used and applied for good purpose and energy savings. Any questions? Oh, we got one. Yes, sir. All right. Please identify yourself and your affiliation and ask your question.
Just one question with the first case study.
Yes?
I didn't see the amount of fresh air that you have in the room, but because you talked before that you need fresh air. In my mind, it was about the fresh air that you need is about 100%, or you have to exchange it. So I didn't see either an exchanger or the induction of fresh air in the diagram that you showed us in the data center.
Well, in that very case, they do not need any heat exchanger because the quantity of heat which is produced inside the computer room is so high that it is necessary to cool in any period of the year, also if it is in the north of Europe. So they have to provide cooling. In the same time, they have also to provide some control of humidity. The cooling, the adiabatic cooling, in fact, it is happening during summertime, where if you have just outdoor air, the temperature inside would come much too high. So they use adiabatic cooling to dampen the temperature into the ambient in summertime. In wintertime, of course, it is 100% recirculated air. Sorry?
You don't recirculate the air. You just put fresh air, cold fresh air inside your room?
Yes, it depends very much on the temperature or control of temperature. According, they fix a certain set point fluctuation. If they exceed, if it is very cold outside, they may recirculate some air in order to keep the temperature at the right value.
If you sign it for them.